Hello everyone, this is my next lecture on dynamics, lecture 13. In this lecture I will discuss two more numericals based on Hooke's law. So the first one is a light spring is kept compressed by the action of given force. When the force is suddenly reversed, prove that the greatest subsequent extension of the spring is 3 times its initial contraction. So the solution is, let OA equal to small l, and in the compressed position we have to make another figure. So in the next figure, let O dash A dash is equal to L be the natural length of the spring. Now suppose the spring is compressed up to B dash such that A dash B dash is equal to small a. This length A dash B dash is equal to small a by a force capital F. This force balances the force of a spring against compression. So by Hooke's law we have F is equal to lambda small a by L. The extension is, here the contraction is small a and L is the natural length. So lambda a by L, give it as equation 1, where lambda is the modulus of compression. Now the spring is released, then it extended up to C dash. When we release the spring, it will extended up to C dash such that A dash C dash is equal to X. This length A dash C dash is equal to small x. Let T be the tension of the spring at C dash, then by Hooke's law T is equal to lambda x by L. Give it as equation 2. Now the equation of motion is m d2x by dt square is equal to F minus T. So substituting the value of F and T from equation 1 and 2, we will get m d2x by dt square is equal to lambda a by L minus lambda x by L. Taking lambda by L common and shifting m from the left hand side to the right hand side, we will get d2x by dt square is equal to lambda by ml in bracket a minus x. Now multiplying both sides by 2 dx by dt, we will get 2 dx by dt into d2x by dt square is equal to lambda by ml into 2 dx by dt bracket a minus x. This can be written as d by dt of dx by dt whole square is equal to minus lambda by ml d by dt of a minus x whole square. Now on integration we will get dx by dt whole square equal to minus lambda by ml a minus x whole square plus a constant c1. So initially dx by dt is 0 and x is equal to minus a because the spring is moving to the other side. The situation is for compression, so we have taken x is equal to minus a. So from here c1 is equal to 4a square into lambda by ml. Substituting this value here, we will get dx by dt whole square equal to minus lambda by ml a minus x whole square plus 4a square lambda by ml. Now putting dx by dt whole square, we will get the required greatest extension x. So in this equation we will substitute dx by dt is equal to 0. So we have 0 is equal to minus lambda by ml a minus x whole square plus lambda by ml into 4a square This implies a minus x whole square is equal to 4a square, taking lambda by ml to the left hand side, it is equated to 0. So after simplification we will get a minus x whole square is equal to 4a square. Using the formula, a minus x whole square is equal to a square plus x square minus 2ax is equal to 4a square. This implies x square minus 2ax minus 3a square is equal to 0. Splitting middle term, we have to factorize this. So we can write it as x square minus 3ax plus ax minus 3a square equal to 0. This implies x into x minus 3a plus a x minus 3a is equal to 0. This implies x minus 3a into x plus a is equal to 0. So either x is minus 3a is equal to 0 or x plus a is equal to 0. This implies x is equal to 3a or x is equal to minus a. X is equal to 3a implies the greatest subsequent extension on the spring is 3 times its initial contraction, and here we have rejected the negative value x minus a. We have rejected this value of x as extension cannot be negative. So x cannot be equal to minus a. Therefore x is equal to 3a, that is the greatest extension of the spring is 3 times its initial contraction. Now the next numerical is show that modulus of elastic string is equal to the force which would stress a light string to twice its natural length. So here AB, this is the initial position as I have discussed in heavy elastic string. You have to see that theorem. This is the application of heavy elastic string. So here AB is equal to small l, B the natural length of the spring whose one end is fixed at a point A and on the other end a weight W is suspended such that its unextended length is A dash B dash such that its extended length is A dash B dash is equal to 2L. According to question, we have to show that that modulus of elasticity is equal to the force which will extend its length to twice its length. So the extended length is taken as 2L. Now let us consider the element P dash Q dash. P dash Q dash is equal to delta X dash. So here we have taken P dash Q dash equal to delta X dash. It is delta X dash at a distance X dash from A dash whose unstressed position is PQ in this case, and PQ, the length PQ is delta X at a distance X from A. Let T be the tension about the element P dash Q dash. Then by Hooke's law, for the element P dash Q dash, the extension will be delta X dash minus delta X and the natural length is delta X only for the element PQ or P dash Q dash, as we have discussed in heavy elastic string. So by Hooke's law, T is equal to lambda delta X dash minus delta X divided by delta X, and from equation of motion, because there is only force in the body is W, so T will balance that force. So by equation of motion we have T is equal to W. Substituting the value of T, we will get lambda into delta X dash minus delta X divided by delta X is equal to W. which can be written as delta x dash by delta x minus 1 is equal to W by lambda. This implies delta x dash by delta x is equal to W by lambda plus 1. This implies delta x dash is equal to W by lambda plus 1 into delta x. Now integrating within the limits 0 to 12 for delta x dash and 0 to L for delta x, we have integration 0 to 12 delta x dash is equal to integration 0 to L W by lambda plus 1 into delta x. After simplifying the integration, we will get 2L is equal to W by lambda into L plus L. This implies L is equal to W L by lambda, and from here we will get lambda is equal to W. That means the modulus of elasticity is equal to the force. In the next lecture, I will start the new chapter, motion in 2 dimensions. Thank you.